So this is the last topic in Chapter 6, and sections 6.1, 6.2, and 6.3 were all about energy. Work, yes, but work gives energy. Kinetic energy, potential energy, elastic energy. We've talked about those types. And now we're going to get on to this idea of power, which is related to energy but different. Okay? So it's related to energy, but it's not the same. We're not going to be using like conservation of power, all that stuff again. And we're going to see that with the units. If you ever have looked at your electric bill, or if you look at units of power in general, anybody know the units of power? Happen to know what the units of power are measured in?
Watts.
It's watts. Very good. Measured in watts. And you would hear somebody say wattage. Wattage is not correct. The word for that is power. If they say how much wattage is produced by that thing, it means how much power is produced. Just like when somebody says how much amperage, amperage is a made-up word. Amps refer to current. So you would say how much current is flowing through the circuit instead of amperage. But just because I've heard the word wattage before. So power is in watts, okay, watts. And we're going to talk about the types of power needed to do certain types of work. So let's go right into this. First, power's definition is really quite simple, actually. And it's going to be twofold here. It is the rate at which energy is transferred. Or is the key, or work is done. Again, the rate at which energy is transferred or work is done. So I'm looking at two definitions of power. I start with power, capital P, equals the change in energy over time. That's the first part of the definition. The rate at which energy is transferred comes from this formula right here. And the second part says, or the rate at which work is done. The rate work is done is simply W over T. The work itself, as a rate, means just divide by time. The delta symbol is there for one T and it's not there for the other. Don't let that confuse you. The definition that your book uses is delta E over delta T. Okay, that's why I leave it this way, and a lot of texts use this. But it's the work over time, really. The work done over a given amount of time. I could find the work done using the work kinetic energy theorem. I could find the work done using FD cos theta. But either way, I can find the amount of work done, or the amount of energy changed in the numerator. The time is always going to be given in these problems, or it's something you're finding. Maybe you're given the power, and you're finding the time. Okay, but the numerator, delta E, or W, is going to be found, write yourself a little note, the numerator of this is found from the 6.1, 6.2, 6.3 ideas. Okay, the numerator is our energy. The numerator is measured in joules. And we see those units are written up here as joules in the numerator. And that's a function of time, or that's related to a rate of time, which is over seconds. So joules per second is what we're looking at right here. Joules per second. And a joule per second is what Steve told us a minute ago is defined as for power, which is the watt. W-A-T-T. Okay, not after J.J. Watt. Different. No football player. Right, J.J. Watt, isn't he a really good linebacker now? I don't know what Watt is actually named after, if anyone wants to look that up. Because usually like certain things are named after either like ohms and stuff, and if we look at like Newton's laws, for Newton itself is named after him. I don't know what Watt comes from, what the derivation from it for. Capital W for Watt, that's one of the reasons I told you already that we didn't use W for weight. The weight of an object, we used Fg, the force due to gravity, because W is used, you're seeing now, for work. It's in the formula. Look, there's a W in the formula right here, and then there's a W over here for watt. So it depends on the context. If it's a capital W in a formula, it means work. If there's a capital W in a formula, it means work. If there's a capital W after a number, it's the unit of watts. You have to use your context to understand what W refers to. Hold on.
Oh, named after James Watt.
Oh, that's what it is? James Watt?
Yeah.
Is he an electrical or some sort of engineer?
Yeah.
Inventor, mechanical engineer whose improvements of the steam engine. That makes sense. In the Industrial Revolution. Okay? Yeah, reason to give him a name, right? Name a unit after him. He's important enough. That actually is really important, the steam engine, but it led to so much more.
Yeah.
Let's jump right into an example of this, okay? Let's get right into the math. This is not a very heavy theoretical topic, you're noticing. Power is just how quickly you do work. Actually, let me give you a quick physical example of this. So, if I were to, I were to use this chair right here as like a step stool, okay? How many of you have seen those corny like aerobic videos from the 70s, right?
Oh, this is the best.
Oh, yeah, I do that all day long. So let's imagine that I'm doing aerobics, right, in an aerobic video, and I do this, right, and come back down, versus doing this. Oh, so what's changing in those two instances? What's the difference that I'm trying to imply? So this is me working out on day 1, and then maybe on day 30 when I do this, right? What's the difference? Physically, what's the difference? Speed. You're doing one faster than the other, aren't you? Isn't it hard? You've all worked out or run at some point or done some physical exercise. It's harder to go faster, isn't it? It's more difficult because you're using more energy. So really, though, you're using more power, it turns out. Everyone answers with energy right away. It's the first answer you want to give. You're using more energy, right? But by definition, the energy needed to do this and step up is the potential energy change, right? So if I do it really slowly, or if I do it really fast, it's the same amount of potential energy change in both cases. But what's different, and look at your formula now from today, what's actually different in the two scenarios? Time. So avoid that misconception. The misconception is that when you work faster towards something, you're giving or using more energy. You're not. You're generating more power, though. That's what makes it harder. Again, I can lift a 25-pound dumbbell from here up to here really slow or really fast. The same amount of energy is used in both cases, the exact same amount of energy, because it's the change in energy, which is potential, the work done by lifting. The work done, whether I lift it slow or lift it really fast, is the same amount of work done, same energy change. So the numerator isn't changing. But by going faster, I'm changing the time period. So if I move faster, is that less time or more time? Let's use logic here. So an increase in speed causes it to take less or more time to do something in general. If you increase the speed that you're working at, it takes you less time. All right, so an increase in speed causes a decrease in time, and a decrease in time causes an increase in power. So these are, and I've used arrows in the past to show implying things. Okay, an increase in speed really means that you're doing something faster, which means it's taking you less time. And look at your denominator. If it takes you less time in the denominator, it means you're decreasing the denominator. If you decrease something that's indirectly related, you're increasing the overall thing that you're looking for. Try numbers if it doesn't make sense. Take a number for energy and pick anything for the numerator, 10, 20, 30. And then keep changing the time value, though. As you change the time value, it's going to change the power generated. So the power is a function of energy, but usually it's the time that's changing that causes you to have more power. Okay, when a car has more, how many of you ever watched Home Improvement? With Tim the Toolman Taylor. Anybody seen an episode with Tim Allen?
Yeah, Tim Allen.
That's right. He would talk about more power in the show. He would just go, oh, more power. He'd always say that. He would try to like soup things up. He made like a dishwasher into like a turbo engine or something. Like, you know what I mean? He always wanted more power. What he's doing is literally increasing the speed at which it's occurring, which is decreasing the time, and decreasing time is increasing the power itself. You're not giving it more energy. You're not taking away more energy. You could be, hypothetically. Like, for example, a long time ago, what was power actually measured in? It was not measured in watts. Think back before cars. That would help you. Give me an answer. What was it measured in?
Strength.
That's a general statement. Horsepower. There it is. Horsepower. So horsepower was your measurement of power that you used. If I have 1 horse versus 2 horses versus 3 horses, it increases the amount of power, really. Because one of 2 ways you can think about it. There's more horses, which give you more energy. For every horse you have additionally pulling on your carriage, you had more energy. So you can think of it as an increase in energy. Increase in energy would increase power. Or you could think of it as, I have more horses, so they'll accomplish the same task in a shorter time period. Right? More horses leads to a decreased amount of time it takes to accomplish the task, which means you've generated more power, more horsepower. Okay, so keep that in mind, that concept of indirect and direct relationships here between energy, power, and time.
Why are light bulbs measuring power?
So the energy that a light bulb consumes is a function of how long you leave it on for, right? So when you go buy the bulb, they can't tell you how much energy you're going to use. They tell you how much energy you use per hour. That's what power is. Because right now, if you go home and on the bulb label it says 27 joules, it wouldn't make sense because energy is based on how long you leave it on for. So there's no way they can give a rating for the amount of energy it will use. They give a rating for how much energy it uses per unit time. And take a look, energy over time, isn't that power? So they give ratings for bulbs like 60 watts. It means it's going to use 60 joules of energy every second. Exactly. You can't be told how much energy you're going to use because it depends on you as a consumer. Some people use no energy in their house because they're good about turning their bulbs off. I grew up with friends and even my family. I would go to my aunt's house in the summer. Air conditioner was always on in every room in the summer, at all times. All times. The house was always like 60 degrees. And yet, my aunt complains about lack of like funding for like money and stuff. I should never read and listen to this, but you know what I mean? You have family that complain about money problems, yet the AC is running 24/7 all summer. I mean, they're literally burning $5 to $10 per day. Just wasted having running the AC all day long. Probably more than that. Besides the contribution that they're negatively impacting the earth with, a whole nother situation, right? You know what I mean? But monetarily, you think about that kind of.
It's more like 15.
Is that what it comes out to be?
It could be more than 15
per day.
per day.
And that's for one unit or for like central?
Unit.
So if we're looking at like 3 or 4 units in a house, you can be dropping like 50, 60 bucks a day.
Because I remember I looked at
It really is. So we're going to do a problem actually when we get to electrical stuff. And we're going to talk about the electricity cost of a bulb.
Yeah, I have like an electric heater in my house and it costs like 3 times.
It's insane. Electric space heaters are the biggest cost higher than air conditioners.
Yeah,
Actually.
whenever I leave it on, obviously.
She'll probably lose her mind. I remember, I remember I moved in, so I'll give you a quick story, college. In senior year of college, we moved into these apartment complexes that were just like run down and old. But me and my 3 roommates, we tried to afford something we could, so we made it work, we rebuilt stuff and all this stuff, we're engineers. And in the senior year, winter hit and we realized, oh, heating doesn't work in the building. We didn't know because it was in the fall and the summer when we signed the lease, right? So we bought space heaters. At this point though, we were paying our own electric bill. And in 1 month, our bill was like $1,400 for electric. There were 4 of us in the room. Okay, and we're talking like in New York City, like space to heat, you wouldn't even spend more than like 100 or 200. My electric bill this month was $52. $52. And I have a 2-bedroom-ish apartment. And it was $52. And we paid $1,400 that month because we all had space heaters. And as idiot engineers, didn't look at the power rating and consumption on them. We just loved the fact that it was like, wow, this warm disk is warming me up, It was great. And then the month hit, we were like, okay, we got to turn these off now. But yeah, certain things are more efficient than others. New bulbs have different power ratings on them for that reason. I don't want to get ahead, and I want to get to this, so let me continue. But electrical power is a little bit different. Same units of watts, but we'll see how it's different later on in the year. So 2 horses pulling a cart. Each exerts a force of 250 newtons at a speed of 2 meters per second for 10 minutes. Calculate the power delivered by the horses, and then how much work is done by the horses. All right. So we did not vary our last formula a little bit. I want to show you something real quick. So here's our definition of power. Power equals the change in energy over time, or let's say for now, work over time. And that was our definition from the last slide. But what we can actually do here is we can alter this a tiny bit. I want to show you that. And it's helpful here because you're seeing right away that we're given stuff with velocity here. So let's see how velocity can play a role and how forces play a role. What's our definition of work? What does work equal? W equals what? What's the formula for work? Good. I'm going to throw a cosine theta in there. If we say that the force is being applied in the same direction of motion, like the horses, I'm a horse, okay? I got the ropes attached to my back. I'm moving and pulling both to the right. So theta would be 0 degrees. And the cosine of 0 is just 1, which makes this formula reduced to FD over T. Okay, FD over T. And what is D over T, though? Distance over time. What does that equal to? Use your stuff from earlier in the year. Yeah, but be more, not velocity. That would be displacement over time. What's distance over time, actually? It's close. It's not velocity. Another word that's like velocity. We've kind of talked about them. Speed. Okay? This becomes force times speed. So this is another formula that could be useful to calculate power. So on the previous slide, I gave you the definition of power as the rate at which energy is transferred, the rate at which, God bless you, work is done. But here we're going to take a look at how this actual formula, work over time, can be changed into force times speed. So let's jot down power equals force times speed. Maybe a little note on the side. An alternate formula for power. Somebody could check if they don't mind on the formula sheet. Do I give you the alternate formula for power? Do I tell you power equals force times speed? I think I do. I'm just not sure. I want to make sure of it. I do? Okay. So on your formula sheet it says power equals force times speed. It's a secondary formula for this. Yes?
How'd you get rid of the cos theta?
Because when I think about the way a horse would pull on a buggy or a carriage, the horse would pull to the right? So that's the applied force is to the right. The motion is to the right. So if I look at two vectors drawn to the right, what's the angle between them? What's the angle between those two lines? 0 degrees. And the cosine of 0 degrees is just 1. Okay, so we're assuming that theta equals 0 in this problem, which is what it's going to be really for these. When you apply force to cause a change in the actual distance occurring there, it's going to be a cosine of 0 degrees, which goes to 1. So this is another formula. So for part A, you're going to see that obviously I gave you this formula now for a reason. For part A, it says calculate the power delivered by the horses. So it's very useful to use this new definition of power to start. Okay, let's use the new definition of power. We're given the amount of force applied by the horses in the beginning. Okay, we're given that value. Here's F, the amount of force applied by each horse. There are 2 horses in this problem, so we can assume how much total force is applied. What assumption do we have to make, obviously? If there's 2 horses. Yeah, so 500 newtons is going to be our force. And we know that the speed that these horses are moving is about 2 meters per second. It's about this fast. Okay, it's pretty quick actually for horses. For humans, it's pretty quick. So 2 meters per second. 2 meters every second. So the power generated is 1,000 watts. So again, a different definition of power. Now we want to look at the other part, and we're going to see how the actual definition we started with comes into play. Yes?
Where do you got 500?
There's 2 horses,
Oh.
each at 250. Yeah, 2 horses at 250 each. So that's where that comes from. Okay. Now, in a problem where this has to do with friction, you might have to replace this F with mu Fn. If it's friction, maybe you have to replace with mu Fn. That's not the case, but keep that in the back of your mind. We've been doing this a lot. We did this in 6.1 with the work, or 6.2 with the work kinetic energy theorem. Okay, so we have to consider the fact that the force is not always going to be given to you. In this case, the force is given. It's 250 per horse. Okay, 250 per horse. Part B says how much work is done by the horses. Well, now we know what the power is. The power is 1,000 watts. Hey, if you're good, you can go. The power is 1,000 watts. The actual time it takes for this to happen was given. I think the time was given as 10 minutes. And the question is, what is the work done? What is the work done? Thanks, Gus. Why did I put an equal sign after 10 minutes? Why do you think I put another equal sign there after 10 minutes? What do you think I'm inferring that you should do? What do you think, Catherine? Convert it to seconds. Anyone know what that would be in seconds? 10 minutes is how many seconds? 600. Because 60 seconds per minute, right? In 10 minutes, we're looking at 600 seconds. So in this problem, we have to remember that our unit of watts is really joules per second. It's our standard units. Joules are the units of watts, or units of energy. Seconds are the units for time. So in this case, we have to have everything in our standard units. Again, we got the power from part A. We got the power from part A. Here's our formula. Power equals work over time. Why am I not using the delta E over time here? Why didn't I delta E?
You're not doing energy.
Yeah, it's not asked about the change in energy. You're not talking about the change in height or velocity to cause energy change in kinetic or potential. But the question says, find the work done. Since the problem wants the work done, let's use the formula with work in it instead of energy. Okay, but work is like energy, right? It's the same idea. So I want to solve for the work done. How do I solve this formula for work done? What does it become to solve for work done? What do I get?
Is it P times T equals W?
There it is. Okay, power times time. The power consumption is 1,000 watts. The time it's on, or the time that these horses are running for, is 600 seconds. So it looks like 600,000, right? 600 times 1,000, hence 600,000. And that'll be in joules. All right, 600,000 joules. Is that reasonable? Can somebody quickly Google convert that? Convert that to calories, right? With capital C, calories, to see how much energy is actually expended. The reason I'm having you convert to calories a lot is because I know you know calories, right? You don't know what the number sense of joules is. But for people that have done exercise before, you burn like 100 calories every time you run a mile or so. So just think about that in the back of your mind. How many calories does 600,000 joules turn out to be? I'm guessing like 150-ish. I'm dividing by 4,000, right? It's around 150. What do you get when you actually? What is it? 143. Okay? So 143 calories of energy. It does not take, first of all, horses are a lot bigger. So 143 calories for a horse is like nothing, right? You're not burning any energy at all, burning fuel. But 143 calories, you're only doing this for 10 minutes. Okay? You're not exerting a lot of force, 250 newtons. So it's a reasonable amount of energy consumption or work done by the horses. Okay, this is again, look at part B. What did it say? It said how much work is done by the two horses. So it's really how much energy do they use, right? This is the work done by the horses or the energy used. So if I had called this capital W, or if I had called this delta E, it's really the same thing still. Again, look up here, please. If I call this delta E and solve for delta E, I get the same answer still, because this is still 1,000, this is still 600. So if I call this delta E or W, it doesn't matter really, because the amount of energy that the horse changes by is the work done by the horse. If I'm the horse and I exert 150 calories of energy in a given period of time here, obviously, it means I'm literally using up the energy in my body as fuel. So the horse will need to eat later to refuel. That's the whole concept of food, and the calories are in and out. Like the calories you take in are burnt for the calories going out. Okay. Let's take the next example to see this. So how much power is needed to lift an elevator if the elevator has a given mass and it travels at a constant rate over a given vertical distance of 100 meters and it takes 15 seconds? So I need you to picture this. Picture the elevator moving. Anything about forces here? Anything about forces? Do you see anything with newtons right away? Anything with newtons, forces at all? So probably not going to use FD cos theta to get work here. It's probably not going to be useful to do that because we have two options when we look at this, right? It says how much power is needed. So here's option 1 and here's option 2. Option 3 we had a little while ago, if we remember, was this. Okay, so I'm going to rule out option 3 right away. The only reason I'm going to rule it out is because I'm not directly given a force. I can figure out the force needed to lift this elevator by looking at the weight of the elevator and given the mass of the elevator. So I could find the weight and go to the forces and find the speed and use that. That works. But I don't want to do it right now. I want to show you a different approach. But I could theoretically use that. I could then pick one of these remaining two formulas, and I could say to myself, well, work done will become FD cos theta. And again, I really don't have the force in this problem, so for now I'm going to rule that formula out also. So in reality, I should really be using this formula, which we haven't used yet. We have not used this one yet. What kind of energy is changing in this elevator if it is moving at a constant rate? it's important to recognize that it's a constant rate. If the elevator were getting slower, excuse me, thank you. If the elevator were slowing down or speeding up from rest, it'd be a whole other ballgame. But it's moving at a constant rate the whole time.
Potential energy.
Only potential energy is changing. If you don't see it, I need you to start to think and picture it. Elevator starts here. Okay? It's already moving. So let's call this the starting point. Okay? It's moving, it's moving, it's moving, it's moving. It starts. It goes up 100 meters, and that's the end of the problem. It never stopped. It never actually started its motion. Imagine it was moving at a constant rate the whole time. So it started here, and it ended here. A change in elevation or a change in height causes a potential energy change. The reason it's important to recognize that it's a constant rate is because if the rate or the speed of it was changing, we'd have a kinetic energy change also, right? So there's no kinetic energy change in this problem at all. There's no kinetic energy change, just a change in potential energy. So when I look at this formula, here's what I'm going to write. I'm going to rewrite the formula for whatever is changing. Just like MEI and MEF, this takes on whatever's going on in the problem. You end with potential energy. You started with potential energy. Therefore, this is the change in energy. There are no other energies in this problem involved. Kinetic energy is the same in the beginning and the end. It's moving at a constant rate, so I don't have to worry about a change in kinetic energy. If I did, I'd have to include that in this numerator. If there was a change in kinetic energy, I'd have to include the initial and final in those spots. There's not. Okay? The constant rate allows me to say that the kinetic energy isn't changing because of the constant rate. All right. With that said, I can go right into my formulas now and think about what I have. Potential energy is mgy. Again, potential energy is mgy. I'm going to give subscripts for each of those. Okay, I'm giving subscripts for each of those. The mass of the elevator is given. Gravity on Earth is 9.81. The final height and the initial height. Okay, so what's the initial height in this problem? What's the initial height in this problem? And if we're not sure, we just draw a little diagram here. What do you got, Clemence?
100 meters.
The initial height. That's the final height is at 100 meters. Okay? What's the initial height considered? Help her out. Help her out. Help her out. No, go ahead. Yeah, it's just 0. Make the problem, remember we talked about this? Make the problems easier for you by calling whatever they start at 0 height. So since this elevator starts somewhere, we don't know where it starts. I have no idea where it physically starts. All I know is that it travels a vertical distance of 100 meters. So I can make this 10 and 110. Take a look. Does that make sense? Isn't that a 100-meter difference? So that would work. Absolutely. What else can I do? I can make this 100 and make this 200. Make this 7,000 and make this 7,100. Right? All of those are changes of 100 meters. But for all of these problems, if I give numbers for both, I have to use this part of the equation, right? But if I call ground level, if I call this instead 0 meters, remember we talked about potential energy reference line? This would be a height of 100 meters, and this would be an initial height of 0 meters. If I call this ground level is always denoted with P equals 0 on the diagram. And it's something we went over already twice now in 6.2 and 6.3. So call this ground level, P equals 0, which means the height is currently 0. The height again is 100. If the height start is 0, it drops this entire thing off, which makes life nice and easy for me. So let's go ahead and cross this off because yi is 0 in this problem, which gives me an overall formula of mgyf minus 0 over time. So I can find the amount of potential energy at the end of the problem, divide it by time, see how long it took to gain that much energy. We have a numerator, 500 times 9.81 times 100, and this is all over a time period of 15 seconds. My units are all good because I look at the values, right? I'm told the mass is 500 kilograms, which is a SI unit. I'm told that the height change is 100 meters, also SI unit. And the time period is 15 seconds, also an SI unit. So these three units are all good. So I know that the power will have the default units to it. The default units to power are watts. Okay, are watts. What do we get here? What do we get?
32,000.
Yeah, 32,000. And a lot of the time you're going to see in texts or in anything that's written, published data, or in your electric bill, things are not usually given in watts. They're given in kilowatts. Kilowatts, okay? Because watts are a very small unit, just like joules are a very small unit, actually. So when you look at your electric bill, we're going to talk about what are called kilowatt hours a little bit later. And that has to do with the amount of energy you actually consume. Kilowatt hours is what it's measured. But this is our answer for this problem. Now, you could have taken a different approach, which I show in the notes, and that approach has you using the work done instead of change in energy. So take a look back at the very beginning if you want. It has you using the top left formula, work done. You could also use the top right formula if you want. So if you want to see a different approach to do the same problem, you could see that in the notes that I have written. Okay, I do want to start at least of one more example here. So we're looking at a problem here with a car. The car is a given mass, 1,800 kilograms. It accelerates in a straight line from a velocity of 3 to 10, both in meters per second, and it takes about 15 seconds to do so. The question is, how much power is delivered? Power delivered. So remember, power is either work over time, or it's change in energy over time, or it's force times speed. So that's my starting point. I have to think about which of these I'm going to use. Power can equal any of those three. What do you think here we should do? What do you think we should do here? Be careful. It's very counterintuitive. It's counterintuitive. What do you think, Chris?
Equals change in E over T.
I like it. Why are you saying change in energy over time? Why would you use that one?
Because it gives you two horizontal velocities.
So what kind of energy change is going to be in this problem? Kinetic energy change. Good. It's very tempting to use F times speed because people see velocities in this problem, right? But what does that speed imply? Write yourself a note. This is when it's a constant speed. Okay, write yourself a note there. This third formula, we're not going to use because the speed is not constant in this problem. This third formula assumes that speed is constant. So maybe write yourself a note that the third formula can only be used when speed is a constant. When speed is a constant. Here it's not, it's changing. So as Chris mentioned, he sees that there's a change in kinetic energy. Now, technically speaking, he's saying to use this, right? Which means this. Okay, everybody see what it means? Take a look. Chris is saying, you know what, use change in energy over time, because there was kinetic energy at the end, and there's kinetic energy in the beginning, and there's time. There's no change in height, so I'm not concerned with the energy of gravitational or potential energy changing. There's no spring involved, so there's no elastic energy concerned with here. So that works, I agree. You could have also technically have used this formula right here. Because what's the work kinetic energy theorem says? It says the work done on an object equals, yeah, which is really just this, isn't it? So inherently, I could have used the first formula if I wanted to and replaced work with change in kinetic energy. But the actual change in energy is kinetic energy. So either way you interpret this is okay in this problem. Okay, recognize that there's no potential energy change here, though. It's all kinetic. And then we just go through the problem. Kinetic energy at the end is 1/2 mvf squared. Kinetic energy in the beginning is 1/2 mvi squared, all over the time period it takes. At this point, it's just plug and chug, right? It's just plug and chug. 1/2. The mass itself is, what number? 1800 times the final velocity squared, which is 10, minus half, 1800, 3 squared, all over the time period of 15 seconds. I don't know why I use 15 seconds a lot. I used that in the last problem also, I just realized, but it's a coincidence, not a recurring thing. The energy change is around 81,000 or 82,000 joules, and that's going to take 15 seconds. Comes out to be 81,900 over 15. And that's the amount of joules in change every second. And joules per second is watts. 5640 watts is my final answer. And again, the numerator is the amount of energy change. That's measured in joules. The denominator is how long it takes. That's measured in seconds. Joules per second are watts. I want to pause it there unless there's any specific questions on this problem. Okay.
Sorry,
Yeah.
where did you get 10 from again?
The final velocity.
Oh.
If it's early in the problem, it says the car accelerates from a velocity of 3 meters per second up to 10 meters per second. So this is the final velocity coming from that, and initial velocity was 3 meters per second where it started.
That was good.
And that was given in the problem. Yep. Yep.
Mine here.
Yes, thank you. Okay, so let's look at the project.